Okay, so a heat exchanger shown in figure 3 is designed to remove heat from the base. The heat exchanger consists of a pool of saturated water and a thin tube. Okay, so saturated water is water heated up to its boiling point. Okay, so any further supply of energy will result it to boil and turn into steam. Okay, from a liquid to a gaseous state. Okay, so any further supply of energy will result it to become steam. And thin wall this thin tube refers to a thin wall tube. So we can neglect conduction resistance across the wall of the tube. The heat rate is 5,000 watts, which is supplied to the base of the heat exchanger and converted to saturate, and is used to convert the saturated water into saturated steam. Okay, so just like what I said, the thin tube has a nominal diameter of 25 millimeters, and is used to condense the saturated steam back to the pool. Condensation on the outer surface is achieved. Condensation on the outer surface is achieved by passing through cold water at a mass flow rate of 0.2, inlet water temperature of 18 degrees Celsius. Assume that the saturated steam pressure is maintained at 30.19 kilopascals. The condensation heat coefficient is this much, and the gravitational acceleration g acts downwards in the downward direction. So, what is the temperature of the cold water at the outlet of the tube? Okay, so why did they specify the g to be downwards? I think this is peculiar to a lot of us. Okay, the reason why they specified g to be downwards, because that some people might interpret this to be the top view of a heat exchanger. So what I mean is, imagine if the heat exchanger was instead, okay, so common sense will tell you that yes, this is vertical and gravity is pointing downwards. But some people might suppose that this heat exchanger, right, is actually the top view of a heat exchanger like this. Yeah, in which case, if the gravity acts downwards, right, then the water should fall downwards like this. Yeah, but instead they want the gravity to fall like this so that the water droplets can drop back down to this saturated water. Yeah. Okay. So anyways, so how are we supposed to do the first question? What is the temperature of the cold water at the outlet of the tube? Okay. What is the temperature of the cold water at the outlet of the tube? So let us first look at the pathway that the energy takes. What I mean is, we're going to consider the conservation of energy. So this 5,000 watts is being used to boil the saturated water into steam, right? So this saturated water will be converted into steam, right? So this is steam. And then after that, this steam will transfer its heat in to the cold water pipe, right? Because inside here is cold water and the steam is really hot. So when the steam touches the cold pipe, it will transfer its heat to the cold pipe, and then the steam will condense back. Okay, condense back into liquid water. So heat is at first being transferred to the saturated water to become steam, and then steam touches the cold pipe, loses heat to the cold pipe. Okay, so this is the control volume for the cold pipe. So the steam loses heat to the cold pipe, and the steam will convert backwards into water. So it will condense on the pipe, okay, condensation, and drop back down to the base, okay, and drop back down to the base. And then it will get collected at the base, and then the base will continue to supply heat at 5,000 joules per second. Okay, so each second, 5,000 joules is supplied to this water, evaporated, and then the steam transfers its heat to the cold water, the steam cools down, condenses, falls back down, and the cycle repeats. Okay, so the cycle keeps repeating like this. So we know that the energy being transferred from the steam Okay, the energy is being transferred from the steam and is used to raise the temperature of the cold water throughout the tube. Okay, throughout the tube. Okay, so whatever temperature change has occurred in the cold water tube, it is because heat is being transferred from the steam into the cold water. And so what we can say is this 5,000 watts effectively is used to heat up the cold water tube. Okay, so at every second, 5,000 joules is being supplied to the cold water tube and raises temperature by some amount. Okay, knowing this, we can write a certain equation. Okay, and what is that equation? So let me show this to you. Okay, so knowing that, we can write. Okay, let me just bring down this question. We can claim that Q dot is equal to mCp TCO minus TCI. Okay, so we know that the 5,000 joules is being used to heat up the water, right? So you put 5,000 on this side. M dot is the mass flow rate that they told us. Cp is what we don't know. We do not know. CO, the outlet temperature, is something we do not know. We know this is 18 degrees Celsius. So we want to find what is TCO, right? Find TCO. That's what the first question is about. But the problem is Cp is a fluid property. Fluid property, we measure at the mean temperature, right? The mean temperature is given by the outlet plus the inlet divided by 2. But the problem is we do not know what the outlet is, right? So we have to assume. Okay, we just have to assume a number. So how did I choose my assumed value of TCO? Okay, how did I choose my assumed value of TCO? First, let us draw the graph of this problem. Okay, draw the graph of this heating problem. Okay, we know that this is a condensation problem, right? Because steam will condense. Okay, yeah, steam condenses on the hot water tube, and you know that condensation or any phase change occurs at a constant temperature, right? So one side will be constant temperature, which indicates that the steam is at a constant temperature, and then another side will be a heating curve. Okay, so this represents the cold water. This represents the cold water. So the cold water heats up, right? Because it gains heat from the steam. So it should move in this direction. Okay? And this is a constant horizontal line. So they told us that the saturated steam has a saturation pressure of 31.19 kilopascals. So if you go to the property tables, you look up saturated water and you go to the you look at the saturated pressure, the saturation pressure column, you will see 31.19. You will exactly see 31.19. And this will correspond, if you look at the table, to a saturation pressure of 70 degrees Celsius. So this is the temperature of steam, right? And then here, the inlet is at a temperature of 18 degrees Celsius. Okay, and we want to know what this TCO is. We do not know what TCO is. We know this is also 70 degrees Celsius because this is a horizontal line. Okay, so that being drawn, okay, so again, we want to beg the question. Okay, let's recap. We want to find Cp, right? Cp is evaluated at the mean temperature, TCO plus TCI divided by 2. We have TCO, but we do not have TC. We have TCI, but we do not have TCO. So this needs to be assumed. And how did I get this assumed number? So we know that, take a look at this. You see that CO, okay, this value of CO lies between 70 and 18. Agreed? It lies between 70 and 18, right? So how I'm gonna make my guess is by taking the exact midpoint of 70 and 18. So we guess, okay, our guess is that TCO is equal to 70 plus 18 divided by 2. Put this in your calculator, you should get 44. Okay, so this is just a guess. Okay, so we guess TCO is equal to 44 degrees Celsius. Okay, so you initiate the problem by starting out with this guess. So assume TCO is equal to 44 degrees Celsius. Okay, then so Tm is equal to 44 plus 18. Okay, so this is the outlet and the inlet temperature of the water divided by 2. Then you get the average temperature of the cold water, which is 31 degrees Celsius. Now, you know that 31 degrees Celsius doesn't appear on the property table, right? So just for the sake of easiness, we can estimate this to be 30 degrees Celsius. Why can I estimate this? Because this 44 was already a guess, so it doesn't have to be accurate. So since this is a guess, you make a guess to calculate out some value. You can sort of round it off so that you can get it in straight away in the property table without any interpolation. Because if you do 31 degrees Celsius, you need to do interpolation. Okay, so let's just round it off to 30 degrees Celsius, which is available in the property table. Okay, so once you guess 30 degrees Celsius as a mean temperature, you find the CP. So CP at T equals to 30 degrees Celsius. You find this on your property table, and you should get 4178 joules per kilogram per Kelvin. Okay. Then what you do is you sub this value. Okay, so sub CP equals to 4178 into the first equation. So this equation, so sub it into 1. So you get 5,000 equals to 0.2 times 4178 TCO minus 18. Okay, so you calculate TCO, you get 23.98. Now, is this correct? How do you tell it's correct? You must compare it to the TCO that you guessed. So the TCO that you guessed is 44 degrees Celsius, right? 44 degrees Celsius versus 23.98. Remember, okay, so let me write down this. Recall, we guessed TCO equals to 44. Now, compare this to the TCO that you calculated and the TCO that you guessed. Are they close? And I don't think so, right? They're not very close to each other. So what you must do is you perform iteration. Okay, you perform iteration. So once you already calculate out 23.98, right? What you do is you use this as your new assumed value of TCO. So at first you assume 44, right? Now you assume it to be 23.98. Okay, but 23.98 is quite a nasty number. Okay, so let's assume, okay, assume TCO is equal to 24. Okay, so this is a nicer number. Okay, so if we assume it is 24 degrees Celsius, then you need to calculate the new mean temperature. So essentially, we're doing the whole process again. So the new mean temperature is, TCO plus TCI divided by 2. So your TCO is now 24, right? So 24 plus 18 divided by 2 is equal to 21 degrees Celsius, which is, if you want to round it off, this is close to 20 degrees Celsius. Okay. I round it off because I want to avoid interpolation. Okay, I want to avoid interpolation. And 20 degrees Celsius is directly available in the property table. Okay, so your CP at 20 degrees Celsius is about 4182. Then after that, you sub this back into okay, so sub CP equals to 4182 into 1. Okay, so 5,000 equals to 0.2 times 4182 times TCO minus 18. Okay, so you can solve for TCO. TCO is equal to 23.97. Now, how do you check if you're correct? To check if you're correct, you compare it with your assumed value of TCO. So the TCO that you calculated versus the TCO that you guessed. And remember, we assume that TCO is 24. Now, 24 versus 23.97. This is extremely close, right? So we can just say that TCO is about 24. Okay, so this is 23.97. We can just round it off to 24. So our final answer is that the outlet temperature is 24 degrees Celsius. Okay, so this is how you do an iteration question. Okay, so iteration question is usually like this. You see a fluid property, and then you need the Okay, they ask you for the outlet temperature. But the thing is, you need the outlet temperature to find the mean temperature, because the mean temperature will help you find the fluid property. But the thing is, now your TCO is unknown and your fluid property is unknown. But the thing is, you need TCO to calculate the fluid property. So what you do is you guess first. Okay, you guess, and then after that you calculate out the value. If the calculated value is far away from the one you guess, then do another iteration. You use the updated value as your next guess. Okay, and then if your calculated value is very close to your guess, then you can stop. Okay, so you say about 24 degrees Celsius. This is just an estimation only. So 24 degrees Celsius, good enough. Okay, so now you know that over here is 24 degrees Celsius. Okay, so now you know that our outlet is about 24 degrees Celsius. So the next question, what is the required surface area of the tube? Okay, what is the required surface area of the tube? And the way to do this, right, there are two ways to go about this. One, you use the epsilon NTU method. Another way is to use the log mean temperature difference method, so the LMTD method. Here, I'm going to choose the LMTD method because it's a lot simpler. Okay, feel free to use the epsilon NTU method. It's okay too. Okay, so let's write down the formula for the log mean temperature difference problem. Okay, so we have log mean temperature difference. Okay, and the value of f, right, is actually equal to 1. Why? Because this is a condensation problem. In the special case of a condensation problem, f is equal to 1. So I don't need to show it here. Okay, now, problem is we do not know what is u, right? We must calculate what is u. Okay, we must calculate what is u. So how do you calculate u? I've done this many times in the tutorial. I think I've done this twice in the tutorial already. So first you draw out the cross section of tube. Please draw it. Okay, please obey my words and draw it. And then you consider the heat transfer, so the resistances, the thermal resistances from the inside the tube to the exterior of the tube. So first thing first is inside this water, inside this cold water pipe, there's convective resistance, right? Because it is heat transfer to a fluid, so there's convection. Then outside of this, there's steam, right? And steam is also a fluid, so that means we have convection heat transfer, so the convective resistance. So this is the outer convective heat transfer, the inner convective heat transfer. What area am I referring to when I say A? The area that I'm referring to is this area. So the surface area of the pipe. So if you want to see this in 3D, this would be the pipe, right? I'm referring to this face. So this area is A. Okay? Okay. So to get U, first of all, we express the heat transfer rate Q dot in terms of the heat transfer, in terms of the overall heat transfer coefficient. This thing is called the overall heat transfer coefficient. Okay, so U A delta T. Okay, so this is one version of the heat transfer rate. Another version of the heat transfer rate is in terms of Ohm's law. So Ohm's law states delta T divided by the total resistance, right? This is just like delta V over R will give you the current. Okay, so what we do is we take equation 1 and we equate it to equation 2. So U A delta T is equal to delta T over R total. Cancel the delta T's, make U the subject. Okay. And then find an expression for R total. So the total resistance, right, is given by the sum of these resistances in series. Okay, so if it's in series, you just add them up straight away. Okay, so you can cancel the areas. So this cancels this and cancels with this. And now we need to sub in the heat transfer coefficients. So meaning this one and this one. So we already know what is HO, right? HO is given to us as 15,000 in the question. here. Okay, so we already know that this is 15,000. But what about HI? HI is inside the tube. The heat transfer coefficient inside the tube. But did you hear me carefully? Inside the tube? How do we find HI? They didn't give it to us. If you remember, inside a tube, right, there's convection. The convection inside the tube or a pipe refers to internal flow. So this is an internal flow problem. Very cunning, right? This is a heat exchanger. But they didn't explicitly tell you to find the convective heat transfer coefficient, the internal heat transfer coefficient. So this is a heat exchanger problem, but then underneath it is an internal flow problem. Yes, there's an internal flow problem combined with a heat exchanger problem. Okay, so let's go ahead and solve this internal flow problem. So find HI. So this is an internal flow problem. Internal flow. So if it is internal flow, first thing first, you need to calculate the Reynolds number. Okay, so you can plug this out of your lecture notes, this formula, for mass flow rate pi d mu. Okay, so we need to find mu, right? And mu is a fluid property. So fluid property, that means you need to calculate the mean temperature. So the mean temperature is given by 24 plus 18, the outlet and the inlet temperature divided by 2, which occurs at 21 degrees Celsius. So now you have to do interpolation. Okay, so please do it on your own. I'm not going to do it for you. So you plug in everything. So 4 times okay, so 4 times 0.2 divided by pi, then the diameter, then the mu, which I interpolated. Okay, you calculate this, you should get 1035.9. Okay, so you see your Reynolds number is 10395.9, which is more than 2300. So this is turbulent. If it is turbulent, that means you use the Dittus-Boiter equation. Okay, you use the Dittus-Boiter equation. So the Dittus-Boiter equation is NUD equals to 0.023 RED 4/5 Prandtl number. Okay, I believe I chose this because this is a heating up problem. And I mean heating up problem in the perspective of the cold water, right? So we're dealing with the cold water tube right now. The cold water is being heated up. That's why I chose 0.4 and not 0.3. Okay, so with that being said, we can plug in the values. So the Prandtl number is also a fluid property which I interpolated. Okay, so if you ask me how do I get it, I interpolate it. So plug in your Reynolds number from earlier. And then your Nusselt number will be evaluated to be 81.122. Okay, so this is your Nusselt number. And remember, once you have Nusselt number, you're only one step away from finding the heat transfer coefficient. The convective heat transfer coefficient. So always remember this Nusselt number relates to the heat transfer coefficient using this formula. Okay, it always relates to the heat transfer coefficient to this formula. So Nu, okay, your Nusselt number and H. Nusselt number and H have a very intimate relationship. Nusselt number and H is always related by this formula. Okay, it's always related by this formula. So now you plug it into here, 81.122 is equal to H. This is unknown, this is known, and then K is interpolated. So K is interpolated to be 0.5998. Okay, so your H is actually HD is your HI, okay, your internal convective coefficient. 1946.28. Yeah, so this is our HI. Now we can plug this back into our formula for U. Okay, we can plug this back into here. So let's recall out U is equal to 1 over 15,000 plus 1 over 1946.28, and then U is approximately equal to 1722.75. Okay, so let's go back to this. The LMTD formula. Okay, the LMTD formula. Okay, so now we have U. We want to find A. We have Q dot. But we don't know what is our log mean temperature difference, right? The log mean temperature difference, just use the formula straight out of your lecture notes. So the formula is given by this TH2 minus TC2 minus THI, TH1 minus TC1 divided by the ln of the first bracket divided by ln of the second bracket. Okay? And next, what you do is you just sum in the values. Okay? Then you punch in your calculator and you get a log mean temperature difference of 48.93. Yes. So finally, you can plot this log mean temperature difference into here. Okay, so let's recall that heat rate formula. So the heat rate formula states UA delta T log mean. Okay, then we know, remember, they told us this one is 5,000. Okay, they told us this is 5,000. And then we already calculated this overall heat transfer coefficient to 2.25. Sorry, 75. My handwriting is trash. Times the area times 48.93. Okay, so A is our only unknown, right? A is the unknown. So solve A. A will be equal to 0.0593. Okay, so this looks like a very suspiciously small area to me. I don't know if I did anything wrong, but yeah, as far as I can tell, it should be conceptually correct. Okay, so if anybody has any disagreements, let me know down in the comments. Okay, but this is how I see the question should be done. Okay, so I'm gonna go on to the next question in the next video. Okay, see you there.